Hey everyone, and welcome to this comprehensive masterclass explainer on object-oriented programming with Java, specifically focusing on Unit 3. I'll be acting as your expert Java instructor today as we go on a bit of a structural journey. We are going to completely unpack the incredible evolution of modern Java. We'll be transitioning from classic foundational object-oriented principles right into the sleek, highly efficient world of functional programming. I mean, this stuff has fundamentally changed how developers write enterprise code. So if you're looking to understand not just the syntax, but the actual underlying philosophy of modern Java, you are in the exact right place.
Okay, let's dive into our syllabus for today. We'll be covering 1. Advanced Java class structures. 2. Interfaces and Lambda expressions. 3. Mastering method references. 4. Processing data with streams. And finally, 5. Modern Java features.
Section 1. Advanced Java class structures. Building blocks.
Right, before we get into the really shiny new functional features of Java, we absolutely have to look at how traditional class architecture has been upgraded to improve encapsulation and logic grouping. Because in Java, you aren't just restricted to putting classes in separate files anymore. You can actually create inner classes. These are classes nested entirely inside another class, or get this, even inside a single method. This is brilliant for helper classes. Think about it. If class B is only ever going to be used by class A, why on earth would we expose it to the rest of the software? By nesting it, you streamline your packages and drastically improve your encapsulation. You do have to remember the strict rules here, though. An inner class can be private, protected, or static, but the main outer class, that can only ever be default or public. And then we also have anonymous classes. These are basically on-the-fly classes without a name, which you'd use when you just need to override an interface method exactly once, without bothering to create a whole new file for it.
Now, closely related to anonymous classes are anonymous objects. The absolute golden rule here is this. An anonymous object means an object without reference, and they can be used only once. Imagine you just need to get the current year. Sure, you could create a new date object, assign it to a variable, and then call getYear. But if you only need that object for that one single action, why store a bulky reference in memory? Instead, you just write newDate.getYear. You instantiate the object and immediately call its method. It has no name, it has no reference, and it does its job perfectly before just being swept away by the garbage collector.
Moving on to another really cool architectural upgrade, we have sealed classes. Look, inheritance is incredibly powerful, but sometimes it needs strict boundaries. If you have a general class, technically anyone can extend it. But logically, a square should inherit from a shape, right? A car definitely shouldn't inherit from shape. Sealed classes allow a parent class to strictly dictate its exact allowed subclasses, and it uses the permits keyword to do it. It's just a fantastic way to prevent unauthorized inheritance and really strictly control your domain model.
Section 2. Interfaces and Lambda Expressions, the functional shift.
Okay, the entire functional programming revolution in Java rests on one critical concept, the functional interface. It sounds intimidating, but it's actually simply an interface that contains exactly one abstract method. Because it only has one unimplemented method, it's often referred to as a SAM, a single abstract method interface. So the crucial point here is this: because the compiler knows there's only one possible action this interface can perform, it allows us to use some absolutely brilliant programming shortcuts, which we're going to see in just a second.
Now, to keep things strictly enforced, we have the functional interface annotation. You pop this at the top of your code, and while it is technically optional, it is highly recommended. Think of it like a bouncer for your interface. If another programmer accidentally comes along later and tries to add a second abstract method to, say, your calculator interface, the compiler will immediately throw a syntax error. Also keep in mind that adding default or static methods, which actually have bodies, doesn't violate this rule. As long as there is only one abstract method, it remains a functional interface.
So why does all this matter? 2 words: Lambda Expressions. Back in the old days of Java, if you wanted to implement a one-off interface, you had to write this really bulky, verbose, anonymous inner class. It took like 5 or 6 lines of code just to write a simple addition function. It was a lot. The modern way uses Lambda Expressions, which you'll recognize by the arrow syntax. A lambda is essentially an anonymous function. It's a function without a name, without a return type declaration, and without an access modifier. It radically, and I mean radically, reduces boilerplate code.
Let's actually walk through how this looks. Imagine we're implementing our calculator interface using a concise Lambda expression. You literally just write calculator C equals parentheses A comma B, arrow A plus B. That's it. The left side of the arrow holds our parameters, and the right side holds the expression.
Notice how we didn't even specify that a and b are integers? We don't need to. The Java compiler is smart enough to automatically infer the data types by looking at the target functional interface. This type inference is exactly what makes Lambdas so incredibly powerful and clean. Now let me pose a rhetorical question for you. How do you upgrade an interface in a massive enterprise application without breaking legacy software? Think about it. If you add a new abstract method to an interface, every single class that implements it will instantly break until you update them. That's a nightmare. Java solved this elegantly by introducing default methods. You can now define a method with the body inside an interface using the default keyword. Older classes just seamlessly inherit this default behavior without breaking, while newer classes can override it if they want to. We also have static methods in interfaces now, which belong completely to the interface itself and cannot be overridden. Section 3. Mastering Method References, the ultimate shorthand. Think about this for a second. Frequently, the body of your Lambda expression doesn't actually do any complex logic. Often, it simply takes the input parameter and passes it directly to an already existing method. Well, if a Lambda is doing literally nothing but calling an existing method, we can condense it even further using a method reference. This utilizes the very cool double colon operator to point directly to a method just by its name. And this brilliantly illustrates the difference. If you have a standard Lambda taking a string s and passing it to the parseInt method, it works, sure. But compare that to the static method reference approach, integer double colon parseInt. It does the exact same thing. It tells the compiler, hey, whatever arguments come in, just hand them straight over to the parseInt method of the integer class. It's shorter, it's cleaner, and it greatly improves code readability. And it gets better because this syntax isn't just for static methods. You can reference instance methods, and incredibly, you can even reference constructors. So instead of writing an empty Lambda just to create a new object, you perfectly replace it with ArrayList double colon new. This is known as a constructor method reference. It's a massive boost in code reuse, allowing you to actually pass object instantiation logic around as if it were just a variable. Section 4. Processing Data with Streams, the API Revolution.
All right, now that we've mastered Lambdas and method references, it's time to see where they truly shine. Enter the Stream API. A stream is basically a sequence of elements that you want to process. But here is an absolutely critical distinction. Streams do not store data. They only process it. A stream operation has a very strict life cycle. Step 1, you pull from a source data collection. Step 2, you chain intermediate operations, like filtering out bad data, mapping elements to new values, or sorting them. And finally, step 3, you hit a terminal operation. A terminal operation like collect, reduce, or count produces a final result and then permanently closes the stream.
Let's meticulously break down a stream pipeline. Say we have a list of numbers from 1 to 6. First, we open a stream. Then, we use the intermediate operation filter with a Lambda to only allow even numbers through. Next up, another intermediate operation, map. We transform the data by doubling the value of those even numbers. Finally, the terminal operation collect gathers our fully processed data into a brand new list. We achieved a complex data transformation in a single, highly readable chain without writing a single manual loop or if statement. How cool is that?
To really deepen our understanding, we can look at complex reductions. For instance, we can use map to int combined with a method reference to quickly unbox our integers, which instantly unlocks powerful math functions, like average. Or if we're evaluating strings, we can call the max function on a stream of fruit names and pass in a custom Lambda comparator to teach the stream exactly how to find the longest string by comparing their character lengths. It's incredibly flexible.
Now, what's really interesting here is the for each method. Traditional Java relied heavily on external iterators, the classic for or while loop, where you manually incremented a counter. The for each method completely eliminates those traditional loops. It acts as an internal iterator. You simply provided a consumer action, like a Lambda expression that prints the item, and the collection itself handles applying that action sequentially to every single element.
Section 5. Modern Java Features. Quality of Life Upgrades. We are wrapping up our explainer today with some standalone modernizations. These are the quality of life upgrades that solve notorious legacy issues and frankly make a developer's daily life significantly easier. First up, try with resources. Before Java 7, reading a file or opening a database connection meant you had to manually write a finally block and call .close. Forgetting to do this caused massive memory leaks. Try with resources automates this entirely. The moment the block finishes executing, it automatically closes the resource for you. Amazing. Then we have switch expressions, finalized in Java 14. These utilize modern arrow syntax, allow you to assign the result of the switch directly to a variable, and crucially, they completely eliminate the need for the break keyword, saving us from those notorious fall-through bugs that used to plague older code bases.
Finally, we have to look at local variable type inference using the var keyword. You no longer have to redundantly declare ArrayList of string list equals new ArrayList of string. It's just too much typing. Now, by simply typing var name equals actu, the compiler instantly infers that it is a string. Var age equals 21 is automatically an int. This ties perfectly back into our overall theme of reducing verbosity and boilerplate, allowing the compiler to do the heavy lifting for you.
We have covered an immense amount of ground today, from the strict structural controls of sealed classes to the elegant shorthand functional pipelines of the Stream API. So I'm going to leave you with this final thought to conclude our masterclass explainer. If modern Java can intelligently infer your data types, completely eliminate verbose loops, and reduce entire classes down to a single arrow, how will you write your next application? Embrace these powerful functional techniques, practice them, and let them transform your code. Thank you so much for joining me on this deep dive into modern Java. Keep learning and keep building.